In the fabric of reality, particles flicker in and out of existence, obeying the unfathomable rules of quantum mechanics. These rules are neither intuitive nor forgiving, but they are consistent until, every once in a while, the universe throws in a twist so peculiar, so entirely against expectation, that scientists can do nothing but take notice. This is the story of strangeness, a property not just of particles, but of the universe's refusal to be simple. Let's journey back to the 1940s. World War II had just ended, and physicists were redeploying their efforts from military technology back into fundamental science. Detectors were climbing into the sky, literally, being installed in balloons and mountaintop observatories to catch cosmic rays, the high-energy messengers from deep space that bombarded Earth's upper atmosphere. When these rays collided with atmospheric nuclei, they unleashed cascades of exotic particles never before seen in laboratories. These were not ordinary fragments of matter. They behaved strangely. Some of them, like the kaons and lambdas, were produced in great numbers during high-energy collisions, which meant they must be formed by the strong nuclear force, an interaction that acts rapidly and ferociously. But after their birth, these particles refused to decay quickly. Instead of vanishing almost immediately, as other strongly produced particles did, they lingered. Tenths of nanoseconds, even hundredths. That may sound brief, but in quantum terms, it was an eternity. It was as if nature was whispering, "There's something else going on here." These particles seemed to violate a basic assumption, that the forces governing their creation would also govern their decay. But here, the strong force created them, and the weak force, far more sluggish, allowed them to fall apart. Even more mysteriously, these particles were always created in pairs. It was as if the universe was carefully balancing an invisible ledger. Physicists were perplexed. They could see the footprints of these particles in cloud chambers, spirals of decay products, tracing elegant arcs in magnetic fields. But the underlying logic remained elusive. Enter the idea of strangeness. This wasn't a whimsical nickname, though it certainly reflected the mood. Strangeness was a proposed quantum number, something like electric charge or spin, that would be conserved in strong interactions, but not in weak ones. That explained everything. Why strange particles were produced in pairs, and why they decayed so slowly. It was a rule not of convenience, but necessity. Without it, the math didn't work. But what exactly was strangeness? To understand that, we have to take a detour into symmetry, one of the guiding principles of physics. In mathematics, symmetry is beauty. In physics, it is power. If a law of nature remains unchanged under certain transformations, rotations, reflections, swaps, then that symmetry often implies a conserved quantity. Noether's theorem, one of the most profound discoveries in theoretical physics, tells us that for every continuous symmetry, there is a conservation law. Strangeness was not born from such a deep symmetry, at least not initially. It was a stopgap, a placeholder. But then Murray Gell-Mann and Yuval Ne'eman began to see a pattern. By arranging hadrons, particles like protons, neutrons, kaons, and lambdas, according to their charge and strangeness, they found that these particles fell into neat geometric groupings. This pattern was so elegant that it couldn't be coincidence. Gell-Mann dubbed it the Eightfold Way, borrowing the name from Buddhism. It classified particles into octets and decuplets, organized by their quantum numbers. And then came the leap. The Eightfold Way wasn't just a filing cabinet. It pointed toward a deeper layer of reality. Gell-Mann proposed that these particles were not fundamental. They were made of more basic constituents. Quarks, 3 types: up, down, and strange. The proton, for example, was made of 2 up quarks and 1 down quark. The lambda baryon, 1 up, 1 down, and 1 strange. Suddenly, strangeness had a physical foundation. It wasn't just a number, it was a count of strange quarks. A kaon carried 1 strange quark, or antiquark. When it decayed into pions, the strange quark had to turn into an up or down quark, a process that could only happen via the weak interaction. And that's why it took so long. With this revelation, the standard model of particle physics began to crystallize. The strange quark joined the up and down quarks as a cornerstone of matter, and more quarks followed, charm, bottom, and top. But the strange quark had a legacy no other quark could match. It forced us to accept that quantum numbers might not always align with intuition, and that conservation laws are sometimes conditional. But strangeness had more surprises in store. In 1964, an experiment studying neutral kaons discovered something that would shake the foundations of physics. These particles could transform into their own antiparticles, and when they did, they violated CP symmetry. The idea that if you flipped a particle into its antiparticle and reflected it in a mirror, the laws of physics would remain the same. That assumption turned out to be wrong. CP violation meant that the universe did, in fact, distinguish between matter and antimatter. And that tiny asymmetry, observed first in strange particles, might explain one of the greatest mysteries of all: why the universe is made of matter rather than equal parts matter and antimatter. You and I exist because of a glitch in the laws of physics, a glitch first uncovered by the peculiar behavior of strangeness. In modern particle physics, strangeness is no longer strange. It is measured, classified, and simulated with astonishing precision. But it continues to open new doors. One of the most intriguing frontiers is the study of strange matter, the hypothetical state of matter in which strange quarks, along with up and down quarks, roam freely in a compressed soup. Such matter could exist in the cores of neutron stars, where gravity crushes protons and electrons together to form neutrons. In these environments, the pressure is so extreme that even neutrons might decompose into quarks. If that happens, the presence of strange quarks could lower the system's energy, making strange matter more stable than ordinary nuclear matter. In theory, a droplet of strange matter, called a strangelet, could convert nearby matter into more strange matter, setting off a chain reaction. This sounds terrifying, but it's highly speculative. No strangelets have ever been observed, and safety reviews of particle accelerators have ruled out the possibility of strange matter catastrophe. Still, the idea remains tantalizing. If strange matter is more stable than the matter that makes up stars and planets, then perhaps entire stars, strange stars, exist out there, dark and dense, humming with unfamiliar physics. Strangeness also continues to challenge quantum chromodynamics, or QCD, the theory of the strong force. The behavior of strange quarks inside hadrons affects everything from particle lifetimes to scattering probabilities. In large-scale experiments at CERN and Fermilab, strange quarks are routinely produced and studied, revealing subtle details about confinement, gluon dynamics, and the structure of the proton itself. And we're still not done. In the early universe, when temperatures were unimaginably high and particles collided with relentless energy, strange quarks would have been as common as up and down quarks. For the first microseconds after the Big Bang, the universe may have been a seething plasma of quarks and gluons, a state recreated today in heavy ion colliders, like the ones at Brookhaven and the Large Hadron Collider. By studying the production of strange particles in these collisions, scientists can learn about the earliest moments of time. Strangeness once a mystery, is now a messenger from the beginning of everything. And so we find ourselves at an unexpected juncture. What began as an inconvenience, a delay in particle decay, became a guiding principle. What seemed like an oddity became a window into the fundamental workings of the universe. Strangeness shaped our understanding of forces, particles, and symmetry. It hinted at the incompleteness of the standard model and pointed toward the great mystery of the matter-antimatter imbalance. Perhaps the deepest lesson of strangeness is this: reality is not obligated to make sense on human terms. Our intuitions are shaped by macroscopic experiences, apples falling from trees, ripples on water. But quantum mechanics lives in a different world, where probabilities rule and identity is fluid. Strangeness is not just a property of particles. It's a property of discovery, a marker of how we respond when faced with the unexpected, a reflection of the fact that even the smallest, most fleeting bits of matter carry with them the signature of the cosmos. In the end, to study strangeness is to confront the unknown, not just in physics, but in ourselves. To embrace the strange is to accept that the universe is far richer, far deeper, and far more wondrous than we ever imagined. And that is perhaps the most beautiful truth of all.